Well, I would like to begin by thanking Brian and Mahir for arranging this conference and for very excellent arrangements here. So it's a pleasure to be here. Now, Brian Conrad has already explained some of the reasons why one should be interested in pseudo-reductive groups if one is interested in algebraic groups or fields of characteristic P, especially the imperfect ones. So I will continue from there, and I would also like to say that pseudo-reductive groups come up when you want to prove some structural properties of general affine algebraic groups. That's not surprising. In fact, there was an announcement by Borel and Titz long time ago where they gave analogs for general affine algebraic groups of conjugacy statements like conjugacy of maximal split tori and so-called minimal pseudo parabolic subgroups and so on, and then Brouwer decomposition. So those results were announced without any proofs in a Conterendu note in 1970s, and there was some outline of the or sketch of the proof given in some lectures by Titz in Collège de France on pseudo-reductive groups. But we worked out all those conjugacy statements and their proofs in our first book, which is going to appear soon in second edition. And our proofs probably are different from, and some are more direct than their proof because we didn't have access to their proof. So that was lucky. So that is one source. So I would like to first mention these books. So first one is the book on pseudo-reductive groups by Conrad, Gaber, Prasad, and the second edition should be out by next month probably. And the second edition is rewritten and quite much bigger in size, so enlarged version of the first one with many new things. And the second monograph, which is going to be soon available by end of the summer, is classification of pseudo-reductive groups and this will be by Conrad and Prasad, and this is going to be available from Princeton University Press by end of summer. And you see the first one gave the general properties and structure and techniques to study pseudo-reductive groups and sometimes even more general affine algebraic groups. But classification was not complete in the sense that in characteristic 2 there were still many questions which were not yet tackled. And in the second edition of this book, we did tackle some questions about the groups with non-reduced root system. In fact, the ones which are pseudo-split were completely described in the new version, and that's the longest chapter in that book. So we will not really be able to tell you too much about groups with non-reduced root system, but I will indicate certainly a few things. But in characteristic 2, there are many more possibilities, and those are all listed in this new book. Okay, so let us begin with some of the properties which pseudo-reductive groups have. So the first thing is that given a pseudo-reductive group, you have notion of pseudo-parabolic, and as Brian mentioned, given a one-parameter subgroup, a lambda from GL1 to G, a homomorphism, you have the notion of PG lambda, where the limits exist under contraction by lambda, and this subgroup is a very nice connected smooth subgroup, and this is called a pseudo parabolic subgroup. It's analogous to the parabolics in reductive case, but when you go to k bar, it doesn't remain parabolic. On the other hand, for a general affine algebraic group, you can still talk of pseudo parabolic, even though the group may not be pseudo reductive. And in that case, what you do is you put in PG lambda the k unipotent radical of the group. So in general, you will put in the k unipotent radical of G, but since we are dealing with pseudo reductive, the k unipotent radical is trivial, so PG lambdas are the pseudo parabolic subgroup. And so the conjugacy statements are that minimal pseudo parabolics are conjugate, to each other over K, just like minimal parabolic over a non-algebraically closed field under GK. And this also allows you to conclude that maximal split tori, maximal K split tori in G are conjugate too. And then you get Brouwer decomposition. Using the Brouwer decomposition in the reductive case, you can get Brouwer decomposition. So suppose I fix a minimal one, so P a minimal pseudo parabolic, containing a split maximal torus S, they all contain a split maximal torus. And in fact, not only they contain a split maximal torus, but whenever they contain a S, they contain the full centralizer of S. So just like in the case of relative case of reductive groups over arbitrary fields, whenever you have a maximal split torus inside a P, then the full centralizer is contained in there. It's also true that intersection of two pseudo parabolics is a smooth connected group which contains some such ZGS. So all those statements hold. Okay, so the Brouwer decomposition says that whenever you have a minimal pseudo parabolic subgroup, you of course, since it contains this, you define WK, the Weil group over K of the system, to be the normalizer modulo centralizer, and that's a constant Ithal group scheme, and its K rational points is it's same as K's rational points, and this finite group is the Weil group of the K root system, which I will define now. K root system of G. So K root system is simply you take on the Lie algebra of G, you take weights, S weights on Lie G except D0. Okay, and that's the K root system. So that's the K root system. Okay, and so one has to prove that this is a root system, and one proves that. And this root system is in general not reduced, just like in the reductive case. So even over separably closed fields, this may not be reduced, which you don't see for reductive groups. So if the group is reductive, the absolute root system, namely the root system over Ks, is always reduced. But not so in one case of pseudo reductive groups. So I will say that in a little while. So in any case, you have the wild group of this root system, and which coincides with the description given for reductive group, namely normalizer bicentralizer. Okay, and then the Brouwer decomposition says that GK, double quotient decomposition of GK is PK and PK union over the normalizer, but on the other hand, you see the centralizer is sitting inside PK, therefore this is a finite double quotient decomposition parameterized by WK. So you have this. You also have this very interesting property, which is same as in the case of reductive groups, namely suppose I give you a root group. So if you give yourself a root group, which Brian attempted to describe last time, but he didn't have time. So suppose I take a root, now absolute or relative. So you have one parameter group inside. So suppose you have one parameter group inside G, then you can take centralizer, and if you choose this one parameter subgroup to be pretty generic, then the centralizer will pick up just one root, in the sense that when you take the centralizer and look at its root system, it will be one character multiplied with integers. Okay? So in other words, you can choose lambda so that so you want to pick up multiples of one particular character, then what you should do is, all multiples, not necessarily integral multiples, but all rational multiples. I mean, there may be half times A, or 1/3 of A is also a character. So so you want to pick up only this, then by fixing a basis of the character group, you make sure that lambda B lambda, this product is non-zero for every B not in QA. Yeah, so then you take the construction which Brian was describing yesterday for every B not in. So you take the construction of UG lambda, and then you will pick up root groups. And then, if root is multipliable, you will have to do something more. You might have to work with some, object which, so suppose 2A is a root and you want to only pick up 2A, not A, then you will take a mu inside your torus such that A is non-trivial on this subgroup mu of your torus. So in any case, you have ways to construct root group, just similar to the way you would do it in case of reductive groups. And now the property which I want to mention is the following. So suppose you have a root, could be a relative root, that is you work with the field K itself, then you will call relative roots. And if you go to separable closure, these are absolute roots. So in other words, you might work with the maximal K-split torus S, or you might work with a maximal torus containing it. So you might work with either, if you are working over K, you will work with this, otherwise you will work with that over Ks. So suppose A is a root, then given an element of UAK not equal to 1, there exists unique U prime, U double prime in U minus AK such that U prime, U double prime lies in the normalizer. Okay, and it acts by reflection. So there is a unique one, and this element acts by reflection. Yeah, so any element which you get this way will automatically act by reflection. So uniqueness doesn't require this property, it will be automatic. Okay, so you have such elements, and it depends on U, so I will call it MU. So you have such elements always in pseudo-reductive groups, and this leads to what is known as Donny. Yeah, I cannot write these things in French. So Donny radicielle generatrice, yeah, how do you say it? The root data, generating root data. So in TIT's language, this is generating root data. So you have that, and this also then gives you in GK a BN pair, carries a natural BN pair. BN pair, in which B happens to be your minimal parabolic rational points of that, and N equals the normalizer of the split torus which we have chosen inside P. Okay, so you get a BN pair for which the Weil group is the relative Weil group with Weil group. So you always have a BN pair. In fact, if you look at the second edition of our book, these things can be generalized a little more, namely not for all affine algebraic groups, but some class which is larger than a pseudo-reductive group, but the essential case is the pseudo-reductive case. In particular, if you are fond of buildings, then you get TITS buildings out of pseudo-reductive groups. And some of these TITS buildings don't arise from reductive groups. In fact, there are lots of Moufang planes, so one-dimensional Moufang polygons, one-dimensional buildings which arise from certain exotic constructions which I will describe, and they don't arise from reductive groups. So one of them was buildings coming from exotic F4. And in our second book, we have a complete classification of those exotic F4s which give you Moufang polygons. The earlier proofs were all very computational, Richard Weiss and TITS. So we have a more conceptual way to construct those examples. But you have whole technology here which gives you all BN pairs and so on. And as I said, some of these BN pairs don't arise. Some of these buildings don't arise from. Now, you probably are wondering whether one can do a representation theory or find maybe new topological groups out of pseudo-reductive groups. And I think someone raised this question last time. So first of all, if you are dealing with rational representations of pseudo-reductive group, then you are going over K bar. And over K bar, a pseudo-reductive group actually is semi-direct product. That's very interesting. You see, in general, an affine algebraic group may not admit a Levy subgroup. In fact, one knows many examples constructing out of bit rings and so on, where you have algebraic groups over K bar and which do not admit a Levy subgroup. Namely, a subgroup L is called a Levy subgroup. A L inside G is called Levy. If you go over K bar, modulo the radical, the unipotent radical, then L inside GK bar maps isomorphically onto this quotient, which is a reductive group. So you have the maximal reductive quotient, namely by the geometric unipotent radical, and L is said to be Levy if over K bar this composite map is an isomorphism. So in general, a affine algebraic group may not contain a Levy. But you know, it's a fact which is very useful for us, and we discovered it early on while writing the first book, is that if you take a pseudo-reductive group, if it's pseudo-split, which means that if it contains a maximal torus which is K split, then it always contains a Levy subgroup. And in fact, the construction I am going to very quickly describe has many useful things in it which are constantly used. And I'm sure some of you can use it in other contexts, because it's a construction which applies to any class of affine algebraic groups. Okay, so it's very lucky that we have Levy's whenever the group has a maximal torus which is K split. So in particular, if you go to separable closure, then G remains pseudo-reductive, but every torus now has become split. So over separable closure, there always exists a Levy subgroup. So unlike the situation with general affine algebraic groups where you may not have Levy, G always admits a Levy at least by going to separable closure. And now then it becomes semi-direct product over K bar, because you choose such a Levy and multiply it with the unipotent radical over K bar. And so G has become semi-direct product. So if you are interested in rational representation theory, and someone was interested in rational representation theory here, then you see semi-direct product, you know, you might look at the vectors fixed under the unipotent radical on which the reductive quotient will act and so on. So there may be some ways to construct some representation theory. Of course, you might have extension problems and so on, so I'm not going to worry about that. But in any case, there is a possibility that you have a good representation theory over rationals. I mean, over rational representation theory. On the other hand, you know, there are some people who are interested in a group, not as an algebraic group, but as a topological group. For example, if K happens to carry a nice topology, like, you know, periodic fields, real fields, complex field, or the function field, a local function field, you know, you start with field with Q elements and adjoin this. So this is a highly non-perfect field, but very interesting. And you might be interested in groups over such fields. These carry topology, and therefore you might want to study not the group G as a algebraic group, but GK as a topological group with topology coming from K. And in Langland's program and in many other fancy parts of modern number theory, you have such groups appearing, and you have infinite dimensional representations of these groups. So now the question would be, so do we get new topological groups, and can we develop you know, some arithmetic or number theoretic questions about these guys. So as a disappointment to you, I should tell you that no new groups arise this way. You see, the reason is that this is one of the basic results proved in our first book is that if you are working with a local or global function field, and if you take a pseudo-reductive group, and if you are only interested in points over k or adelic points, then these topological groups, either the adel group or the group or local field, these topological groups are topological groups arising from an honest reductive group. So attached to any pseudo-reductive group, there are some reductive groups. As we will see, over a larger field, you go to reductive quotient, and then you build from there. So the topological groups which arise this way are no different from what you have already seen before. So in that sense, and also Galois cohomologically. So Galois cohomology, if you are only interested in these fields, then the Galois cohomology problem about these groups can usually be translated to problems over reductive groups for reductive. So in some sense, pardon me?
This reductive group
is L, but over a restriction of scalars of L. Not L, but restriction of scalars.
There is some issue with commutative stuff.
So there will be, as always, issues with commutative stuff, but we have already been forewarned about that. I'm ignoring that.
Can I also ask you, if you take G mod L?
L is not a normal subgroup. Yeah, L is just a Levy subgroup. In fact, it cannot be normal. Okay, now other thing which I want to say is that just like in when you are working with a non-algebraically closed field and you want to classify reductive groups, so the general scheme of classification is that you do things over separable closure, and as Brian's t-shirt showed you all those Dinkin diagrams. So those Dinkin diagrams classify up to central isogeny all algebraic simple groups or separately closed fields. Now the question is how to get groups classified over the given field. I'm interested only in fields which generally are not separately closed. So classification over Ks is not good enough for me. So I want to get classification over K. Then you see, for reductive groups, the beauty is that you have a Chevalier group already defined over the base field of that type, and then you have the question of some Galois cohomological translation means that you want to classify H1 of the automorphism group. Or there was, you might want to classify H1 K or G. Okay, so this will classify. So you start with a say Chevalier group G naught of that type, and you go to the automorphism group of G naught, and then H1 of this will classify all adjoint groups of that forms which become isomorphic to the given one over Ks, because over Ks A and B and C and D, and they almost uniquely give you the classification up to central isogeny. So you will use that. So there are two problems with this. First of all, this cohomology set is very easy to explain even to an undergraduate student, but in practice it's very hard to compute even for very nice fields. Even over reals, Eli Kartner had to do some work before he could compute these things. And certainly over number of fields, whole class field theory can be translated to say that this is, computing this object for GLN. So, the computations are not easy, but you have a convenient language, and you have certainly over good fields, good results. So for pseudo-reductive groups, the problem is that there is no analogous split form. So as some examples presented in our second book show, that even very small groups, type A1 groups, can fail to have a split form. Namely, you may not have a pseudo-split group which becomes isomorphic over separable closure to the given group. So the translation to this problem is a little more delicate. On the other hand, there was this famous article by Tits, which is, in volume 9 of Symposia in Pure Mathematics, AMS Symposia in Pure Mathematics. This SAGE classification of semi-simple groups. And in this article, one technique used in classification is that you classify groups in terms of what is called the anisotropic kernel. So what you do is you start with a maximal split torus embedded in T as before, and then you take the centralizer of S. So this is probably a huge reductive group in itself. See, in general, if S is not T, then centralizer of S is in general a very large non-abelian reductive group. So in the case of pseudo-reductive group, the centralizer is still pseudo-reductive and it is still large, non-abelian generally, and its derived group is now, I don't know how to call it, say M prime. So this derived group is called the anisotropic kernel because this group has no split tori in it. So in that sense, it's anisotropic, its K rank is 0. So Tits classification was in terms of, you have diagram of the root system over Ks, namely using T. And on this diagram, so let us draw one diagram. So you have, let's say, type for E6. Okay, so you have this diagram, let's say type E6, and then you have this diagram is with respect to T. So the Galois group operates on the character group of T because T is not split, so it operates often non-trivially. And of course, it may change the basis to some other basis, but you can bring one basis to another by a transformation coming from the Weil group. So that gives rise to a star action. So Tits had this star action. So you have a star action, and in this diagram, the star action can only be this going to that and this going to that. So you have the diagram with the star action. And Tits conveniently described this diagram now by folding the diagram. So this is our E6 diagram folded to show that these two roots which are close to each other now are in the same star Galois orbit. And similarly these two, and these guys are isolated. They don't have they don't move under the star action. So these are called Tits indices, but now he also wants to locate inside this diagram how M prime sits. So M prime is a subgroup. In fact, the centralizer of S contains T, and therefore M prime is normalized by T, and therefore root system of M prime is contained in the root system of our original group, and you describe the position of M prime inside by circling roots which should not be there in the diagram of M prime. So for example, in this picture I have not circled these two, so M prime is of type A2 because these two roots give you a A2 system. So this locates M prime inside the centralizer, inside the group G. at least, yeah, in some sense. Okay, so these roots which are circled are called distinguished roots. So the TITS classification proceeds as follows. You have a diagram on which there is a Galois group acting through star action, and you have a way to locate your M prime. Equivalently, those roots are called distinguished if their restriction to S is non-trivial. So you locate S or M prime by putting circling around distinguished roots. And what this diagram is nowadays called the TITS diagram or TITS index of the group. So this is TITS index of a group of type E6. Of course, it does not rebuild E6. The reason is that this anisotropic group of type A2, we do not know what this A2 is, because A2 can be constructed out of Hermitian form in 3 variables or cubic division algebra and so on. So there are many ways to build a group of type A2, and which way this A2 has been built only God knows in this particular situation. Maybe he even doesn't know. So that is, there is a big ambiguity here. So TITS classification says that in some sense describing M prime in this diagram tells you everything. So the ambiguity is in describing M prime. So if you knew the in some sense isomorphism class of M prime, and if you knew this diagram with the Galois action and distinguished orbits, then you know the group. So you can, with some effort, you can also carry out this classification for pseudo-reductive groups. So you have TITS type classification. Of course, the main difficulty in any such classification is that given such a diagram, what M prime can be realized inside a given group as the anisotropic kernel. And that's a very deep question. For example, whether this E6 exists over Q or some such field. For example, if I take separately closed field, of course such a E6 doesn't exist. But even over for example, over some very nice fields, this E6 may not exist. So the reason is that there may be no cubic division algebra, or there may not be an anisotropic Hermitian form in 3 variables. So there are serious problems about existence, and TITS classification doesn't address those problems in general, but with the help of Kneger, who knew arithmetic of algebraic groups very well, he was able to, over good fields, decide which M prime can really appear over good fields. So that problem, of course, is difficult, and one cannot pretend to answer those. Okay, so now, having said all this about the general facts about rational points and classification and so on, let us now see how Leverage can be constructed and what the construction involves, which is quite a useful thing. So actually this construction was inspired by a paper of Steinberg which he gave me when I visited UCLA. I was not aware of this paper, and but it became quite useful. So you see, the construction is the following. So this is very general G, any smooth connected affine group. So I will forget to write smooth connected. So you have a affine group over K. Yeah, so you see, Steinberg of course works over K bar. But the realization is that you can work things out over a non-algebraically closed field with suitable hypothesis. So suppose you are given a split torus inside here. So inside here I am given a split torus, not necessarily maximal one. Okay, so we are just given a split torus, K split torus. And of course, you will take non-trivial one. Gabor will insist to take non-trivial one. But if you get trivial one, you will get trivial output. So I'm not worried. Okay, and then you take C to be some smooth connected group, subgroup containing S as a maximal split torus. Okay, at the same time, I look at the character group of S, and inside that, I take a linearly independent subset, So linearly independent over Q, tensor with Q. Okay, and now let's assume that for each A in delta, I'm given a subgroup FA. A smooth connected subgroup. Okay, which contains C. And when you take the centralizer in FA of this split torus S is contained in C, which is contained in FA. So when you take the centralizer of in FA of S, you get C. So this is a maximal split torus inside FA then. Now the question is, if I take the group generated, so there is one more restriction, and the root plus minus A is a root of FA relative to S, and all other roots of FA relative to S are contained in integral multiples of A. Yeah, those are the conditions. So FA, each subgroup FA given from delta contains C, and the centralizer of S is precisely C inside FA. And the roots of FA are, first of all, plus minus A, I want it to be root, and secondly, I want the roots to be not too many, just integral multiples of A. You can apply this to reductive groups. Take a favorite reductive group, and you will find such systems very, very quickly. Okay, now I also want to assume that for A not equal to B in delta, the root group, A root group in FA commutes with minus B root group in FB. Once again, for reductive group, suppose you take two linearly independent simple roots, then this will happen, because A minus B is not a root. If you have two simple roots, then the difference is not a root, therefore they commute. Okay, then the group generated, group F generated by FH has very nice properties. So let me list some of these properties. You know, after all, F is generated by FH, which are smooth groups. Therefore, F is smooth, connected, everything. But moreover, S is a maximal split torus. S inside it is maximal split. So you don't get anything larger. Also, the root groups of F, for any A, the A root group of F is same as that of FA. So for each A in delta, the root groups, a priori may have become bigger, but that's not the case. Also, suppose you assume that F wedge were all split, namely S was actually a maximal torus, not only maximal split torus. Then it would follow that your group F will be split. And suppose you knew that F wedge are all pseudo-reductive, then the group F will be pseudo-reductive. Any interesting property you might have for F wedge is carried over by F. So this is a nice way to construct groups. For example, there in this very famous old paper of Borel and Titz on reductive groups. So they construct inside a reductive group a split subgroup of same rank. Yeah, and in fact, in that paper, this is the most difficult result. If you consider by length of a proof the depth or hardness of a proof, this is the longest proof there. Okay, so now you can prove this easily. Now see, if you have a reductive group, you take its relative root system and declare delta to be a basis of that relative root system. Now for all roots which are not multipliable in delta, you pick up an SL2. And the one which is multipliable, the root system may be BCN because I am working with relative root system. Then if you have a multipliable root, then for that multipliable root B, you have 2B as a root. So you take SL2 in the 2B, and the group which you construct from this is that group. So this is a very general way to construct. Also, the group F is functorial in FH. So in other words, if I have two groups G and G prime, so if I have two groups G and G prime, and inside this you have torus S, S prime, which are somehow isomorphic, abstractly isomorphic. I'm not saying that G and G prime are isomorphic. I'm just saying that S and S prime are abstractly isomorphic. And suppose you have fixed delta and delta prime here in the character group, and you have fixed an isomorphism which moves delta to delta prime and vice versa. And suppose you have a choice of FH and C inside here, C prime inside here as we want, and FA and FA prime where A and A prime correspond under this isomorphism. Then the group which you construct here and the group you construct here are isomorphic. So if these happen to be isomorphic, carrying C to C prime, then you get an isomorphism. So this way you recover the famous classical isomorphism theorem for reductive groups. Because SL2s, a reductive group over K bar, that's what Steinberg was interested in. So you build isomorphism between two reductive groups, provided they have the same root system, and if the SL2s match. So this is a proof. Okay, so this theorem, which is theorem C2.29 in our book now, is a very important result. Okay, so this is in the appendix C. I mean, I'm just joking because it's a useful theorem, so one remembers the name in the number. Okay, at least for now. So in any case, so let us see how this produces Levy subgroups. So in case of reductive group, as yesterday Brian was saying, you have SL2s. Now in case of pseudo-reductive group, things are not so nice. I mean, you don't have SL2s, but things are not so bad either. And for each root, you certainly have root groups. And these root groups are pretty nice. These are vector spaces, at least over Ks, and things work out very well. So if you have, for example, a pseudo-split group, G, then what you do is you fix a maximal, now I will denote it by T, a maximal torus instead of maximal split. So maximal torus, which is K split. Now you take, for the root system, you fix a basis. So you take the root system of G with respect to T and you fix a basis. Now having fixed a basis, you consider U sub B and U sub minus B, these root groups for B in delta. And if B is multipliable, so if B is not multipliable, so in other words, if 2b is not a root. Otherwise, you will take u minus 2b if 2b is a root. That's the only possibility in a root system. If b is multipliable, the only multiple can be 2b, as you know from study of root system. So if b is not multipliable, you consider this group. If it's multipliable, then you consider this group. These are pseudo-reductive groups of rank 1 inside. Now, actually, these are independently vector spaces, ub and u minus b, on which the torus T acts linearly by homothety. So what you do is in ub you fix a line. It's a vector space, so you fix a line, with this linear structure. And having fixed this line, now you go back to the construction of given a element u, you can find u prime and u double prime such that the product u prime, u double prime, you remember mu I introduced, the French 3 words, donner, rediciel, generatrice. So, that gave you an mu. Okay, so now you fix a line in ub, and using that normalize, the element in the normalizer which takes b to minus b, it acts by reflection in b. So you get a opposite line inside u minus b. And these two things generate an SL2, we prove, or PGL2. And you do it for each b in delta. So you have bunch of GL2s and PGL2s, depending on whether the group is simply connected or not, and sometimes even in non-simply connected group you will get PGL2. So in any case, you have very nice subgroups, F sub A, and they are all normalized by T. So you declare your C, which I need in this theorem, C2.29, you declare your C to be just T, nothing more. And